There is a moment in every modern city when the illusion of permanence begins to crack, not with explosions or visible collapse, but with silence. The tap turns, and nothing comes out. No warning sirens, no dramatic countdown, just absence. The most dangerous part of a water crisis is that it begins long before anyone notices. By the time a city feels thirst, the system that sustained it has already been failing for years, sometimes decades. Water infrastructure does not collapse overnight. It erodes quietly through overuse, miscalculation, population pressure, and environmental limits that were ignored because they moved too slowly to trigger alarm. And right now, across the world, multiple urban systems are approaching that invisible threshold. The core danger is not scarcity alone, but the mismatch between demand and replenishment. Cities are not built on water. They are built on assumptions about water. Engineers design reservoirs, aqueducts, and pumping systems based on historical data, rainfall averages, and population projections that often fail to account for extreme variability. When those assumptions drift even slightly from reality, the system begins accumulating stress. At first, the imbalance is absorbed through reserves, groundwater extraction, or temporary conservation measures. But these are buffers, not solutions. Once those buffers are depleted, the decline accelerates, and recovery becomes exponentially harder. Most people misunderstand how water systems actually function. The common belief is that water is either present or absent, as if supply is a simple on-off condition. In reality, water availability exists on a spectrum governed by complex feedback loops. Reservoir levels fluctuate seasonally, aquifers recharge over decades or centuries, and distribution networks lose significant volumes through leakage and inefficiency. A city can appear stable on the surface while its underlying system is already in deficit. This is why water crises often feel sudden to the public, even though they are the result of long-term structural imbalance. The hidden science behind this lies in hydrological lag and infrastructure inertia. Aquifers, for example, do not respond immediately to changes in rainfall. If an aquifer has been overdrawn for years, even a period of above-average precipitation may not restore it. In some cases, overextraction causes land subsidence, permanently reducing the aquifer's storage capacity. This means the system does not just lose water, it loses the ability to hold water in the future. At the same time, aging infrastructure introduces inefficiencies that compound the problem. Pipes leak, treatment plants degrade, and energy costs for pumping increase as water sources become more distant or deeper underground. Evidence of this systemic strain is already visible in multiple global regions. Satellite data shows declining groundwater levels in key agricultural and urban zones. Long-term reservoir monitoring reveals downward trends that are not explained by short-term drought alone. Urban expansion continues in areas where water availability is already overcommit, creating a structural deficit that cannot be corrected without either reducing population pressure or drastically increasing supply, both of which are difficult to achieve quickly. These are not theoretical projections, they are measurable realities. The survival implications are profound because water is not just another resource. It is the foundation of every other system, from food production to energy generation to public health. When water supply becomes unstable, the effects cascade rapidly. Agriculture contracts, increasing food prices. Energy production falters where cooling water is required. Sanitation systems degrade, raising the risk of disease. Economic activity slows, property values decline, and migration patterns shift as people move away from unstable regions. The crisis does not remain isolated. It spreads through interconnected systems. What makes this situation more urgent is the rate of escalation. Population growth continues in many high-risk cities, increasing demand precisely where supply is becoming less reliable. Climate variability amplifies extremes, making wet periods shorter and dry periods more intense. Infrastructure, often decades old, struggles to adapt to conditions it was never designed to handle. This creates a compounding effect where multiple stressors converge at the same time, pushing systems closer to failure thresholds. And this is where the transition begins, from a general global pattern to specific urban realities. Because while the dynamics of water stress are universal, their outcomes are local. Some cities have diversified supply systems, giving them time to adapt. Others depend heavily on a single source, making them far more vulnerable. The difference between resilience and collapse often comes down to how many failure points a system can absorb before it breaks. The cities that follow are not chosen at random. They represent different failure modes within the same global crisis. Each one illustrates how a modern urban system can approach water instability from a different direction, whether through depletion, contamination, overdependence, or infrastructure decay. And in each case, the warning signs are already present, measurable, and accelerating. The first city exists in a paradox of abundance and fragility, where water appears plentiful until the system beneath it is examined closely. It is a coastal metropolis expanding faster than its infrastructure can adapt, drawing heavily from groundwater that is now being infiltrated by forces it cannot control. The danger here is not drought, but contamination through saltwater intrusion. As sea levels rise incrementally, the boundary between freshwater and seawater shifts inland, pushing salinity into aquifers that once supplied millions with drinkable water. The analysis reveals a system built on a shallow geological foundation, where porous rock allows rapid movement of water but offers little resistance to contamination. Many assume rainfall is enough to compensate, believing that frequent storms will naturally replenish supply. This misunderstanding ignores the physics of pressure gradients and density differences between saltwater and freshwater. Once saltwater penetrates an aquifer, reversing it is extraordinarily difficult. The hidden science lies in hydrostatic balance, where denser seawater forces lighter freshwater upward and away from extraction zones. Evidence from monitoring wells shows measurable increases in salinity over time, confirming that the process is already underway. The survival implication is stark. Even if water remains physically present, it may no longer be usable. This shifts the crisis from quantity to quality, which is often harder to solve. As intrusion advances, treatment costs rise, infrastructure must be redesigned, and entire supply zones may be abandoned. The escalation is subtle but relentless, and it transitions into a broader pattern where cities dependent on single-source groundwater systems face disproportionate risk. The next case illustrates a different failure mode, one driven by over-reliance on a single aquifer that cannot sustain the scale of demand placed upon it. This is an inland urban center experiencing rapid population growth, where nearly all water is drawn from underground reserves formed over thousands of years. The danger is depletion without immediate visibility. Unlike reservoirs, aquifers do not provide clear visual indicators of decline. The analysis shows extraction rates exceeding natural recharge by a significant margin, creating a deficit that compounds annually. Many residents assume that groundwater is effectively limitless because it is out of sight, reinforcing a dangerous misconception. The hidden science involves recharge cycles that depend on specific geological and climatic conditions, often requiring decades to restore what is removed in a single year. Once water levels drop below critical thresholds, pumping becomes more energy-intensive and economically unsustainable. Evidence includes declining well outputs, increased drilling depth requirements, and regulatory triggers that impose restrictions during low-level conditions. The survival implications extend beyond water access to economic stability, as industries reliant on consistent supply begin to falter. Agriculture contracts, urban development slows, and competition for remaining resources intensifies. Escalation occurs when drought conditions coincide with already stressed reserves, accelerating the timeline toward critical shortage. This leads directly into the next scenario, where depletion has already occurred and the system survives only through external dependence. In another city, the local water supply has effectively been exhausted, forcing reliance on imported water transported over vast distances. The danger here is systemic dependency on infrastructure that extends far beyond the city's boundaries. The analysis reveals a complex network of canals, pipelines, and agreements that deliver water from distant sources, often hundreds of kilometers away. Many assume that engineering solutions guarantee reliability, underestimating the vulnerability of long-distance systems. The misunderstanding lies in equating technological capability with resilience. The hidden science involves loss factors such as evaporation, leakage, and energy requirements for transport, all of which increase as distances grow. Evidence shows declining input levels at source reservoirs combined with rising demand at the destination, creating a widening gap. The survival implications are immediate if disruption occurs, whether through mechanical failure, environmental change, or policy shifts. A single break in the chain can interrupt supply to millions within days. Escalation becomes inevitable when multiple stressors align, such as reduced upstream availability and increased downstream consumption. This sets the stage for a broader regional crisis, where interconnected systems begin to fail simultaneously rather than independently. Another urban center demonstrates the risks of diversification without stability. It draws water from multiple sources, including rivers, aqueducts, and groundwater, creating an appearance of redundancy. The danger, however, lies in the simultaneous degradation of all sources. The analysis shows that each supply line is subject to its own set of pressures, from declining snowpack to regulatory constraints and environmental degradation. The common belief is that having multiple sources ensures security, but this ignores the possibility of correlated failure. The hidden science involves climate patterns that affect entire regions rather than isolated locations, reducing the effectiveness of diversification when all sources are linked to the same environmental drivers. Evidence includes reduced flow rates, lower reservoir levels, and increased competition among users sharing the same. The survival implications are complex, as managing multiple declining sources requires balancing allocations in ways that often lead to shortages across the board rather than stability in any one area. Escalation accelerates when infrastructure designed for historical conditions cannot adapt to new extremes, leading to more frequent breakdowns and inefficiencies. This transitions into the most extreme cases, where a single source dominates and its decline dictates the fate of the entire city. In the final scenario, a rapidly growing metropolitan area depends overwhelmingly on one major reservoir system that is steadily shrinking. The danger is concentration of risk, where the failure of a single resource triggers immediate and widespread consequences. The analysis highlights a mismatch between population growth and water availability, with demand increasing while supply trends downward. Many residents believe conservation efforts alone can resolve the issue, overlooking the scale of the imbalance. The hidden science involves long-term hydrological cycles and allocation agreements that distribute water across multiple regions, often based on outdated assumptions about availability. Evidence shows declining reservoir levels, reduced inflows, and increasing evaporation rates due to rising temperatures. The survival implications are severe because there is no viable alternative source to absorb the shortfall. Escalation becomes unavoidable as thresholds are approached, where intake systems can no longer function effectively and emergency measures are implemented. At this point, the system transitions from managed scarcity to potential structural failure, where recovery is no longer a matter of conservation but of fundamental redesign.